Yeah, hello viewers, welcome to Teleconference organized by Department of Mathematics, Dr. B.R. Ambedkar Open University. Today in Teleconference, so we are discussing about the residues theory. So this is in the complex analysis is the one of the topic residues theory. The students of PG second years year-wise system they are studying, and as it is similarly PG first year second semester students. So the semester is started from this academic year 25-26. So this is very important topic in further your examination after complete the PG, when you are writing the CSR, NET, SET or GATE, whatever may be, the complex analysis is the very key for your all the students. So today we are going to the total 1 hour session, that is 60-minute session. So first 40-minute sessions, so there are the experts are there. So they are explaining what are the residues theory, what are the singularities. So remaining 20 minutes. So remaining 20 minutes, so you can interact with the experts through telephone. So remember one thing, so the telephone number is 040-23-680-456. So once again I repeated 040-23-680-456. So now today we are going to discuss about the complex analysis. In the topic is residues theory. So before that, what is the complex numbers? So in the number system, generally we know all of you they are thinking what real analysis is the biggest set in the number system, but there is one more set is there, that is the complex number system. So that's we can write that is in the form of a plus r minus ib, and that I equal to under root of minus 1. So generally in the previous studies this we can tell imaginary numbers. So today we are going to introduce the experts. So here the one of the experts will be there, Professor K. Phaneendra, Department of Mathematics, Osmania University, Hyderabad, and one more experts will be there, Dr. S. Rakmaiah, Associate Professor, HOD of Department of Mathematics, Vignana Bharathi Institute of Technology, Hyderabad. Yes sir, good afternoon sir.
Good afternoon.
Yes sir, now you can tell what are the use of the residues theory and what are the singularities and how it is useful for general problems. Yes sir, you can start.
Yeah. Dear students, today topic is residues. Residue means in general language it is called remainder or error. Whenever we talk about the numerical methods, error that is also named as residue. But in complex analysis, residue stands for it's a remainder, and these residues plays an important role to evaluate an improper integrals, right? Some in real analysis, in real integrals, some improper integrals are there. For example, minus infinity to infinity x square plus 5 by x power 4 plus 2x plus 8, or something sin x by x square between 0 to pi by 2, like that. Some improper integrals are there where we cannot evaluate them in natural process. So this residue theory is very useful to evaluate such type of integrals. And before going to define the residue, we need the definitions of analytic function and singularity. Generally, a complex valued function f of z equal to u plus iv. For example, see, these are the contents of this today's topic lecture. And before going to singular points, let me explain about the function, analytic function. The function f of z is said to be analytic if at a point z equal to a, z is a complex number, at a point z equal to a, if that function f of z is differentiable at that point, and in the small neighborhood also it is differentiable. Okay, and differentiability is different from analyticity. Differentiable function means it is differentiable. If, for example, y is a function of x, differentiable function means dy by dx exists. When f of z is analytic function means its derivative f dash z is continuous, as well as f double dash, f triple dash and all derivatives are continuous. Okay, this is the main difference between differentiability and analyticity. Okay, now when a function is analytic at a point and at every point of a domain, for example, if I take some domain, at every point of a domain, if the function is analytic, the function is called entire function, analytic everywhere. Okay, now if in that domain there is one such a point where the function is not analytic, ceases to be analytic, such a point is called singular point. Exactly, this is the singular point here. This is the singular point. The definition of singular point is f of z is not analytic, ceases to be analytic at that point. Now see, for example, we have taken one example, f of z equal to 1 by z minus 2. Clearly at z equal to 2 the function is not defined. Function itself not defined means it is not differentiable. So z equal to 2 is a singular point. Now in at z equal to 2, take a small neighborhood of z equal to 2. That means 2 minus delta to 2 plus delta, a small subinterval, that is called small neighborhood of 2. So small neighborhood of 2. Then what happens? In that small neighborhood the function is analytic, but at z equal to 2 it is not analytic. In such case, that means what? At z equal to 2 is only the singular point, but in small neighborhood there is no other singular point. Then such singular point is called isolated singular point. Isolated singularities are two types. One is isolated singularity and the other one is non-isolated singularity. And for this example, z equal to 2 is the isolated singularity. Exactly what I explained here. In the neighborhood of z equal to a, there is no other singularity except z equal to a. Now see this one more example. Here the function f of z is z plus 2 by z minus 1, z minus 2, z minus 3. Okay, here see the function is not defined at z equal to 1, z equal to 2, z equal to 3, right? So there are three singular points, 1, 2, 3. If I take one small at the point 1, if I take small neighborhood, these points 2 comma 3 does not belongs to that small neighborhood. So one is isolated singular point. Same logic for z equal to 2 and z equal to 3. Those are the isolated singular points. Now see, this is one of the best example. F of z equal to 2 by sine pi by z. 2 by sine pi by z. See, what are the singularities here? Singularities are sine pi by z equal to 0, isn't it? Sine pi by z equal to 0 means when this will be 0, sine n pi equal to 0. So z must be plus or minus 1 by n. Yes, exactly. When z equal to plus or minus 1 by n, the sine pi z is what form? Sine n pi structure. Sine n pi is always 0. So z equal to plus or minus 1 by n are the singularities. Means what? N is 1, 2, 3 and so on, right? When n tends to infinity, this 1 by n tends to 0, isn't it? So the singularities are what? From minus 1 to plus 1. Many singularities are there. 1 is there, 1 by 2 is there, 1 by 3 is there, right? 1 by 4 is there, like that many singular points are there. Now the thing is here, at the point z equal to 0, if I consider a small neighborhood, obviously 1 by 10, minus 1 by 10 or plus 1 by 10, there are some singular points are there in the neighborhood of z equal to 0. Exactly, this z equal to 0 is not isolated singularity, right? So it is a non-isolated singularity. That was mentioned here. The origin z equal to 0 is singularity, but it is not isolated. Why? Because in the small neighborhood of z equal to 0, there are other singularities of the given function. Now, the main concept of residue comes from the Lorentz series expansion. Generally, when f of z is analytic function, we can express in terms of Taylor series, and another one is Lorentz series. Taylor series is in a domain D, but Lorentz series is in a ring shaped region. That means annulus. That is region bounded by two subregions, right? So the statement of Lorentz series is z equal to a is an isolated singularity of a function f of z in what region? In a circular region. What is that? 0 less than mod z minus a less than r. Means what? The radius will be what? A plus r minus a plus r, like that, in which f of z is analytic only in this ring shaped region. What is the domain? Mod z minus a less than r, right? Then f of z can be expressed as summation n equal to 0 to infinity a n z minus a whole power n. And see the second term, summation n equal to 1 to infinity bn z minus a whole power minus n. Means what? The first term involves positive powers and the second term involves negative powers like z minus a whole power minus 1, z minus a whole power minus 2 and so on up to infinity. Means positive power series plus negative power series defines as a Lorentz series. Okay, defines as a Lorentz series. If for example in this series expansion, if bn value is completely 0, when bn equal to 0, f of z is what? Summation a n z minus a whole power n. That means this first term only, right? When this first term will be there, it is nothing but Taylor series. It is nothing but Taylor series. And in this one, now let me explain. For example, yeah, the singularities are here for this Lorentz series. There are three types of singularities. One is removable singularity, another one is essential singularity, another one is pole. Okay, removable singularity. In name itself, the word is there, removable. Means what? We are removing the singularity. In this removing the singularity means what? Here, what happens here? In this removing the singularity means this second term is there na, negative power series, which is called principal part of the series expansion. If bn value is 0, then what is this? Z minus a whole power minus n. That means 1 by z minus a whole power n terms will not be there, right? 1 by z minus a whole power n means z equal to a will be the what? It's a singularity. When bn value 0, this entire term will collapse. That means we are removing completely the singularity. That means if the Lorentz series expansion does not contain any negative powers, exactly when bn equal to 0, the singularity z equal to a is named as removable singularity. Exactly the definition is mentioned here. See, f of z, the principal part means negative power series of f of z contains no terms, that is bn equal to 0 for all n. Then the singularity z equal to a is called removable singularity, and that case f of z can be expressed as only in power series, positive power series, right? Now see, always if a function is given, how to identify removable singularity or pole or essential singularity, some short techniques must be there. It is not always possible to express any function as a positive power plus negative power series. So one short definition, shortcut technique is what? The z equal to a is called removable singularity when take limit of this function f of z as z tends to a. It must be a finite constant. It must be a finite constant. You can substitute here, it may be 0 or a positive constant or a negative constant. Then z equal to a is called removable singularity. See this example, suppose sin z by z. Let me take one example here. F of z equal to sin z by z. Sin z by z, clearly this function is not defined at z equal to 0, isn't it? That is z equal to 0 is what? Singularity. Z equal to 0 is singularity. But what happens when z equal to 0? What is this function is of the form? It is equivalence to 0 by 0 form. At z equal to 0, the function is having 0 by 0 form. And at intermediate level, we know that limit z tends to 0, sin z by z, its value is 1, sin theta by theta value is 1. Exactly this is the short definition. My function is f of z. I am taking z equal to a equal to 0 as the limit, right, point. When this value, it is a finite constant, that means my z equal to 0, what type of singularity? Removable singularity. But how it is possible? Let us see. Since let me take this sin z by z. What is the expansion of sin z? Taylor series expansion of sin x. This is x minus, in place of x, z is there, z minus z cube by 3 factorial plus z power 5 by 5 factorial and so on whole by z. Then I will take z common from the numerator, then that becomes z square by 3 factorial plus z power 5 by 5 factorial and so on whole by z. Now what is sin z by z becomes 1 minus z square by 3 factorial plus z to the power of 5 by 5 factorial and so on. See, is there any negative series is there in this one? This is my f of z equal to sin z by z, right? Since we are expanding, what expansion is about? Sin z expansion of sin z about what point? About the point z equal to 0. Means what? Since this is contains only positive powers and no negative power is there, clearly z equal to 0 is what type of singularity? Removable singularity. It is a removable singularity. This is one example. For example, let me try one more example. If my function is of this structure, f of z equal to z into e to the power of 1 by z, z into e to the power of 1 by z, this is also a function. Now, I don't know z equal to 0 is singularity or not, I don't know. What type of singularity, that also I don't know. I can't identify. If I take limit value, my short technique, limit z tends to 0, z into e power 1 by z, that means what? 1 by 0 infinity e to the power of minus infinity. So, I will take minus for this one. Now, let us see what happened. What is this one? What is this value? Now, let me expand this. Z into, I know the expansion of e to the power of x. What is that? 1 plus x square by factorial 2, x cube by factorial 3 and so on. So, let me utilize that expansion here. In place of x, minus 1 by z is there. So, 1 minus 1 by z plus 1 by 2 factorial into z square and so on. This is my expansion. Let us take z inside. Z minus 1 plus 1 by 2 factorial z. Next term is what actually here? 1 by 3 factorial z cube. Exactly here 1 by 3 factorial z square will be there, and next and so on. That means what? Here see, z terms are in denominator. Means what? This constant is here plus z power 1 positive power is there plus 1 by 2 factorial z power minus 1, 1 by 3 factorial z power minus 2, something z power minus 3 and so on. That means this expansion is having what? Positive terms as well as negative terms. How many? Infinitely many. So, since negative terms are there, here z equal to 0 is not a removable singularity. Not a removable singularity, isn't it? I think now it is clear how to identify removable singularity. Now, what is this? Now, when a Lorentz series expansion contains infinite number of negative terms, what is like this? Infinite number of negative terms, then z equal to that singularity, z equal to a is called essential singularity. This is named as essential singularity. Essential singularity. Okay. Now, this is the second part. First one is removable singularity and the second one is essential singularity. And let us see third one, pole. Pole of order m. Pole of order m. What is the pole of order m? I know my Lorentz series expansion. What is that? Sigma an, right? Z minus a whole to the power of n plus bn z minus a whole to the power of minus n, isn't it? Right? Both are n equal to 1 to infinity, 1 to infinity. Here 1 to infinity, but this term is not 1 to infinity in my pole. This is some up to some finite terms. Means what? The series is like that. If I substitute here, this is 0 if I take a naught plus a1 into z minus a plus a2 into z minus a whole square. These are all positive terms plus coming to negative terms. What is this? b1 z minus a whole to the power of minus 1, b2 z minus a whole to the power of minus 2 and so on. What is my last term? m. Exactly, that is bm into z minus a whole to the power of minus m. If my Lorentz series contains negative powers up to m, negative powers up to m, right? Up to m, negative power series exist. Negative power series exists. Then z equal to a, this point, this is, I can write this term as what? 1 by z minus a whole to the power of m, isn't it? Right? So, z equal to a is called pole of order m. Z equal to a is called pole of order m. Pole of order m. Now, one more simple definition. A pole of order 1. A pole of order 1 is called simple pole. This is named as simple pole. That means what? Pole of order 1 means in negative power series how many terms exist? Only one term exists. What is that? That means f of z becomes what? This positive powers are there, many are there, n is from 0 to infinity, but only one negative term is there, that is up to minus 1. Okay, this is called, then the z equal to a is called, here z equal to a is called simple pole. This z equal to a is called simple pole. Okay, these are the main singularities. One is removable singularity, another one is essential singularity, which contains infinite number of negative terms, and another one is pole of order m. Negative power series contains up to m terms. Now, according to this pole, essential singularity, and for removable singularity, since there is no remainder terms, all are infinite, but pole of order m, there is a residue, and for a essential singularity, the residue. What is that residue? See, I have written this term, right? Z minus. Let us multiply on both sides by z minus a. What happens? See, f of z equal to summation. This is a n z minus a whole to the power of n plus 1 plus b1 only. Plus b1 only. Now, what I will do? Let us take limit z tends to a. That is z minus a into f of z. Z minus a into f of z. Limit z tends to a means this first term will become 0. So, only b1 will be there. That is my b1 value. This is called residue. This b1 is called residue of f of z at a point z equal to a. Sometimes one can write residue at z equal to a, or residue of the function f of z at the point z equal to a, that is b1. Always in Lorentz series expansion, b1 stands for residue. B1 stands for residue. Okay. Now, this is the definition of residue, and in Lorentz series formula we have some coefficients formulae, a n value and b n value. A n value is 1 over 2 pi I integral over c f of z by z minus a whole to the power of n plus 1 dz. This is quotient of a n in Lorentz series, and the quotient of b n is 1 by over c. This is f of z by z minus a whole to the power of minus n plus 1 dz. Right, these two quotients. Then if I put in b1 value, what happens here? What is b1 equal to? 1 over 2 pi I, right, integral over c f of z by, this is n equal to 1 means what? The z minus a whole power 0, that is 1. So, this b1 value is what? 2 pi I into integral over c f of z dz, isn't it? Therefore, my integral, at the beginning of introduction I told you what is the benefit of residue, to evaluate some improper integrals. Exactly, this is my evaluation of integral. F of z is some function, integral over c f of z dz value is what? 1, what is this? This is 1 by 2 pi I. So, 2 pi I into b1. What b1 stands for? 2 pi I into residue of f of z at z equal to a. This is evaluation of integral when it has a simple pole. When multiple poles are there, not a single pole. A1 is one pole, A2 is one pole, AN is one pole. There are many poles are there. There is one domain D here. There is a pole here, there is a pole here. Pole is nothing but singularity, isn't it, right? A3 and so on. Like that, if n singularities are there, then this formula becomes n singularities are there. Then what happens? This integral over c f of z dz. F of z dz is 2 pi I into what I said here previously, residue of f of z at a. Exactly, residue at a1 plus residue at a2, z equal to a2, and so on, residue at z equal to an. This is nothing but 2 pi I into sum of the residues at poles which lies only inside the domain, which lies only inside C, inside, this is curve C, right, inside C. Exactly, this is so called, what is this theorem named as residue theorem. This is theorem named as residue theorem. That is integral over C. This integration of a complex valued function is evaluated by using residues. How? 2 pi I into sum of the residues at each pole, where each pole lies inside that one. Outside pole we don't require any residue. Wherever pole is inside, calculate the residues at each pole and apply this residue theorem formula. I can evaluate any type of integral. form, integration, improper integration. This is about residues. Now let us go to the PPT. Yeah, see, this is another example. Yeah, this example I have told you, removable singularity. This is Lorentz series expansion, and this is a pole of order. I told you this is short technique. What is that? For a function f of z multiplied by, if a pole of order n will be there. For simple pole, what we did, f of z multiplied by just z minus a. Now this f of z multiplied by z minus a whole power n and limit taken as z tends to a, if that one is a constant not equal to 0, finite constant not equal to 0, then z equal to a is called pole of order n. And one more short formula, what is that? If my function f of z, if my function f of z is, if it can be expressed as a form phi of z by psi dash psi of z, phi of z by, that is a rational function, then residue of f of z at z equal to a, there is a formula, that is phi of a by psi dash a, phi of a by psi dash a. This is a formula provided that psi dash a is not equal to 0 for the existence of residue. This is one more short formula when function is expressed as phi of z by psi of z structure. Okay. Now the formula is mentioned here, and this is I explained already, essential singularity, right? Now if I want to study what is the residue of f of z at z equal to infinity point, not z equal to a, z equal to infinity point, a simple logic is what? In the function f of z, you replace z by 1 by z something, z equal to 1 by something. Then what is z tends to infinity means what? This z tends to 0. So f of z at z infinity, problem is now is equivalent to f of 1 by z at z equal to 0, right? Now at z equal to 0, find the residue, automatically you will get at z equal to infinity, you get the residue of f of z. Okay. Now my colleague Rakmaiah will take over the session.
Alright. Now, so we are discuss about the limit point at pole and limit point of a zeros. So for example, suppose z is equals to a is a limit point of the sequence of poles of analytic function f of z, then every neighborhood of z is equals to a which contains a poles of the given function. So therefore the point z is equals to a is a singularity of that f of z, so that this is not a pole, since it is not isolated, which is not isolated. So such singularity is called non-isolated singularity or non-isolated essential singularity. So non-isolated essential singularity is nothing but at the point z is equals to a, at that point only, so which contains every neighborhood of that point contains one or more other singularities are exist, then that is called non-isolated singularity. So at z is equals to a has only one singularity, does not contain any other singularity other than z is equals to a, then that is called isolated singularity. Now let us discuss about limit of that poles and limit of that zeros of the functions. For suppose a function f of z, for suppose a function f of z e power of z has how to behavior of that isolated, non-isolated at the point of z is equals to infinity, right? So for suppose I would like to choosing here f of z is equals to e power of z, f of z is equals to e power of z. Now the behavior, what is the behavior of this function f of z at z is equals to infinity? Let us discuss about this now. So the behavior of the function f of z at z is equals to infinity, the behavior of the function f of z at z is equals to infinity is the same as f of 1 by z at z is equals to 0. So the behavior of the f of z at z is equals to infinity is the same as the function f of 1 by z at z is equals to 0 here. Now our function is choosing for that f of z is equals to e power of z na. So at z is equals to infinity na. So now to substitute instead of z 1 by z. So that is f of 1 by z is equals to e power of 1 by z. Okay. So at z is equals to 0 here. Whatever it is, the behavior of f of 1 by z is the same as the f of z has the behavior of z is equals to infinite. Now we know that, just now to discuss about that e power of z. So we know that e power of z expansion, so that is 1 plus z, e power of 1 plus z plus z square by 2 factorial plus z cube by 3 factorial plus up to so on z power of n by n factorial, well known. Instead of z, just have to substitute e power of 1 by z, that is 1 plus 1 by z plus 1 by z square into 2 factorial, 1 by z cube into 3 factorial plus up to so on 1 by z power of n into n factorial. Now, so this can be written as here 1 plus summation n is equals to 1 to infinity 1 by z power of n into n factorial. Now, just now to discuss about that Lorentz series expansion. Now, so here e power of 1 by z can be written as here two parts. So that is, one is the analytical part and second one is the principal part. So that is, here one is the analytical part. So and the second part is the principal part. About z is equals to 0 here. So e power 1 by z should be right into the form of 1 plus summation n is equals to 1 to infinity 1 by z minus 0 whole power of n into n factorial. So this is called principal part. This principal part having infinite number of terms are there. So if it is an infinite number of terms are there according to the definition of the essential singularity. So about z is equals to 0, which is a essential singularity. So that at z is equals to 0 is essential singularity of this function f of 1 by z is the same as the at z is equals to infinity our function f of z is equals to e power of z has essential singularity about z is equals to infinity. In the same function, I would like to choose another function, that is f of z is equals to e power 1 by z at z is equals to 0 here. About at z is equals to 0 here. Now the same function, again to express this function f of z is equals to 1 plus summation n is equals to 1 to infinity 1 by z minus 0 whole power of n into n factorial. Yes or no? So at z is equals to 0 is expansion. How many number of terms are there in the principal part? Infinite number of terms are there. So that at z is equals to 0, our function f of z is e power of 1 by z has essential singularity. Now let us go for that discussion about the next problems. So next we will go for that. Yeah, so in the PPT, so we can find the which kind of the singularities of the function following functions. First one, cot of pi z by z minus a whole square at z is equals to a and z is equals to infinity. Let us discuss about this function cot pi z by z minus a at z is equals to a and z is equals to infinity. See here. So I will go for this discussion about this function. So let us consider our function f of z is equals to, we know this, cot pi z by z minus a whole square at z is equals to a and z is equals to infinity. Let us discuss about that singularity of at z is equals to infinity and z is equals to a of this function f of z. Yes, we know that cot is nothing but a cos by sine. So we can rewrite this function cot pi z should be right into the form of cos pi z by sin pi z into z minus a whole square. Now to find out the singularities of this function. So what is the singularities of function here? The denominator should be is equal to 0, then we can get some points. That points are called automatically, which is fails to the analytic function. So now we can equating to the denominator value should be equals to 0 here. So that is sin pi z is equals to 0 and z minus a whole square which is equals to 0 here. Now to find out the singularities, sin pi z is equals to 0, then how much of value is that pi z? So we know that we know that if it is sin z is equals to 0, then automatically z is equals to n pi. So where n belongs to integers. Integer is nothing but here 0 plus or minus 1 plus or minus 2 up to so on. Now here sin pi z is equals to 0, sin pi z is equals to 0, that implies pi z is equals to n pi, n belongs to integers here. So here pi is cancelled in both sides now, so then z is equals to n. So n belongs to here integers, then and z is equals to n as n tendings to infinity. Now we can observe here limiting value as n tendings to infinity, then z is equals to infinity. Z is equals to infinity. So just now to seen here, the limiting value of the pole is non-isolated essential singularity. Non-isolated essential singularity. So therefore z is equals to infinity is limiting. So limit of the function, limiting of the function about that singularities. So therefore at z is equals to infinity has non-isolated essential singularity. Non-isolated essential singularity of that our function. Now so we have another singularities are there now. So what is that? Z minus a whole square equals to 0. Then if it is z minus a whole square is equals to 0, so that implies z is equals to a comma a here. So here it is a finite values are there, then automatically these are the poles. So in the principal part of the Lorentz series expansion having the finite numbers, then automatically it is a pole. So therefore it has a finite number of the negative terms, then automatically z is equals to a comma a is the finite. So this is called the pole. Now these poles, now at the point of z is equals to infinity, then these poles are called must be a zeros of that function. Okay, so now let us go for that another problem here. So that is f of z is equals to sine of 1 by 1 minus z at z is equals to 1. So what happened? The singularity of this function sine of 1 by 1 minus z at the point of z is equals to infinite. So just now to see now poles, limiting value of the poles should be is non-isolated now. So the zeros of the limit points are must be a isolated singularities. So now we have to find out the zeros of this function. So what is our function here? Sine of 1 by 1 minus z. So the zeros of this function, f of z is, that is sine of 1 by 1 minus z, which is equals to 0. Now just now to see now sine z is equals to 0, then sine z is equals to 0. If it is, then z is equals to, just now to see n pi, where n belongs to all integers. So instead of that z, we have here 1 by 1 minus z. 1 by 1 minus z. So therefore 1 by 1 minus z is equals to n pi, where n belongs to integer here. Now we need to find out here z. So that is 1 minus z is equals to reciprocal 1 by n pi, and n belongs to here z here. Z is nothing but integer here. So what is the 0 plus or minus 1 plus or minus 2 up to so on infinite values. Now so we write z is equals to 1 minus 1 by n pi. So where n belongs to integers here. Now we have to find out the limiting value of this zeros. So that is as n tendings to infinity, then we can get z is equals to 1. Simple, because as n tendings to infinity, then automatically 1 by n which is tendings to 0 now. So then automatically 1 by n pi which is tendings to 0. If we have one, instead of 1 by n pi value, that value equals to 0 here. So therefore z is equals to 1 is isolated singularity. So therefore at z is equals to 1 is isolated singularity. So now let us discuss, we have to discuss about this now, the continuation here. So this problem, right now, so what kind of the singularities we have the following the functions. These functions, let us discuss about that, which type of singularities are exist here. So let us discuss. First one is 1 by sin z minus cos z here. 1 by sin z minus cos z. So discuss about this problem. Now So given function f of z is equals to 1 by sin z minus cos z at z is equals to pi by 4. Now let us discuss about this singularities of this function f of z here. Okay, so the singularities of function 1 by sin z minus cos z na, so the denominator value equals to 0 na, so that is the singularities of f of z is given by sin z minus cos z, which is equals to 0. Simple. So sin z minus cos z is equals to 0 na, so therefore sin z is equals to cos z, sin z is equals to cos z, and cos z taken to left hand side, that is the tan z, sin z by cos z is equals to tan z is equals to 1. If it is the tan z is equals to 1, then z is equals to pi by 4 plus n pi, and n belongs to all integers here. Okay now, so at z is equals to pi by 4 plus n pi, for all n is equals to integers 0 plus or minus 1 plus or minus 2 up to so on here. Now the singularity of this function z is equals to pi by 4 is a simple pole. So therefore at z is equals to pi by 4, our function f of z have simple pole here. Okay, so now similarly we can discuss the same problem about sin z minus cos z about the z is equals to infinite. So let us discuss about the function. Next problem, f of z is equals to sin z minus cos z, the same function about z is equals to infinity. Let us discuss the singularity of this function here. Now, so the zeros, so f of z is equals to sin z minus cos z na, so we can get the zeros. The numerator value it is equating to 0, then we can get the zeros, and denominator value equating to 0, then we can get the singularities. So therefore f of z is equals to 0, that implies sin z minus cos z, which is equals to 0. So the same thing here, sin z that is tan z is equals to 1, just now it is seen here, then z is equals to pi by 4 plus n pi, and n belongs to integer here. So these we have to apply the limit. So as n tending to infinity, then we can get z is equals to infinity. So that obviously we can get at z is equals to infinity is isolated essential singularity. Okay now, so these are the problems to discuss about the z is equals to infinity. So like that only we can discuss number of problems here. So now continuation of our PPT here. So these are the problems. So similarly we can get here. So next third one is f of z is equals to z square by 4, z square plus 4 by e power of z. Then we can get f of z having for that plus or minus 2 high is the simple poles. Similarly 1 minus z by fourth one, 1 minus z by 1 plus z. Now we here also denominator value should be equals to 0, then we can get the singularities e power of z. Yeah, so we let us discuss here 1 plus e power of z is equals to 0 na. So 1 plus e power of z, so that is our function. Next fourth one, our function f of z is equals to 1 minus e power of z by 1 plus e power of z. Okay, so the singularity is 1 plus e power of z is equals to 0, then e power of z is equals to minus 1, but e power of z is equals to minus 1, then z is equals to logarithm of minus 1. But logarithm of minus 1 which is not defined in the real, but whereas complex we can define here logarithm of minus 1 should be defined here logarithm of mod minus 1 plus I times of argument of z plus 2n pi. So where n belongs to here integers here. Argument of z, what is the z value here? Z is equals to here minus 1. So therefore argument of z, that is argument of minus 1, that value equals to pi. We know that. So therefore z is equals to, so logarithm of minus 1 is nothing but 1. Log 1 is 0. So therefore I times of argument of z is pi plus 2n pi, and n belongs to z here. So therefore e power of z is equals to minus 1, then z is equals to pi plus 2n pi into I. So these are the isolated singularities are there here. Now coming to our main topic is residues. So just now to see our eminent faculty is discussed about that residue. So residue at the poles. Now let us discuss about that poles of residue at poles. See, suppose a function f of z having the single variable. So the pole of order m at z is equals to a. Then by the definition of the pole, according to the Lorentz series expansion, the principal part having the finite number of terms are exist here. So we have to use for that f of z is equals to summation n is equals to 0 to infinity an into z minus a whole power of n plus summation n equals to 1 to infinity bn into z minus a whole power of minus n. So here we can go for that principal part is a finite now. So instead of this infinity, here we have m. Okay. So now where the coefficients are defined here, what are the coefficients here? an 1 by 2 pi I integral over c f of z into dz by z minus a whole power of n plus 1. So whereas bn is equals to 1 by 2 pi I f of z by z minus a minus n plus 1 into dz here, where the c is must be a circle mod z minus a equals to r here. Now the thing is, if I had to substitute in the coefficient n is equals to 1 in bn, so bn is equals to, we know na, so instead of n we have to substitute 1, then we can get here b1 is equals to 1 by 2 pi I integral over c f of z. So the residue is the coefficient of 1 by z is called the residue at z is equals to 0 here. Now the coefficient of 1 by z minus a is always residue at the point of z is equals to a. So that is a simple. So the residue which is denoted by res at z is equals to a or residue at f of z at z is equals to a here. Now so consider, so some special cases are there, then how to find out the residues. So if it is the poles are simple poles, then we know how to find out the directly by using the formulas. And if it is the pole of order m, then you can find out the residue at that pole only. Okay. So if it is a residue, see this here, our function f of z residue at pole by the Lorentz series expansion, f of z is equals to finite pole means here principal part is finite na, so that is summation n is equals to 0 to infinity an into z minus a whole power of n, okay, plus summation n is equals to 1 to m, so bn by z minus a whole power of m. Okay na. So if it is n is equals to 1, we can get f of z is equals to summation n is equals to 0 to infinity an into z minus a whole power of n, then we can get b1 by z minus a. So now to multiply with z minus a on both sides and apply the limit at z tending to a, then we can get residue at z is equals to a when z have a function having that simple pole. So that is z minus a multiply with on both sides and apply the limit z tending to a. So we can get here summation n is equals to 0 to infinity an into z minus a whole power of n plus 1 plus b1, and as z tending to a here, so in the first term is 0, so we have here b1 only. So therefore b1 is equals to, according to that, 1 by 2 pi I integral over c f of z into dz. So that is nothing but our residue at a simple pole. We can write into the form of b1 is equals to 1 by 2 pi I integral over c f of z into dz here. So according to that, our continuation process, so let us discuss residue at z is equals to infinity. Then how to find out? In the finite complex plane we can find out the same thing here. In the residue at infinity, so that is nothing but our function should be extended complex plane. So we have to choose the point z at z is equals to infinity in the extended complex plane. So simple, very simple, f of z is an isolated singularity at z is equals to infinity na, so which is the analytic. Then the residue at z is equals to infinity, which is defined, residue at z is equals to infinity is nothing but minus 1 by z coefficient of our Lorentz series expansion, only 1 by z minus a coefficient only. So that is nothing but residue at z is equals to infinity is nothing but instead of b1 just have to multiply with negative, then we can get residue at z is equals to infinity. So that is minus 1 by 2 pi I integral over c f of z into dz. So this is the residue at z is equals to infinity. So just now sir is explained about that Cauchy's residue theorem. So what says the Cauchy's residue theorem here? The integral over c f of z into dz is equals to 2 pi I into sum of the whose singularities are inside of that circle here. Now let us discuss about that residues, how to find out the residues at finite poles and at infinity only. So let us choose the first problem here. Evaluate the residue z square by z minus 1 into z minus 2 into z minus 3 about singularities z equals to 1 comma 2 comma 3 and at infinity. So let us discuss about this point here. So this function here, so take one problem, f of z is equals to z square by z minus 1 into z minus 2 into z minus 3. So let us discuss the residues of this function, their singularities. What are the singularities are there here? So the denominator value should be equals to 0 na. So at z is equals to 1, 2, 3 are the singularities, So let us discuss singularity at residue at z is equals to 1. Our function f of z is equals to 1. So that is limit z tending to 1. So that is z minus 1 into our function f of z. Yes or no? So simple. So limit z is z tending to 1. So z minus 1 into z square by, so that is z minus 1 into z minus 2 into z minus 3 here. Okay. So z minus 1 is cancelled na. So limit z tending to 1 is nothing but here 1 by 1 minus 2 into 1 minus 3 here. So that is 1 by, so this is a minus 1 into minus 2, that is 1 by 2. Now the residue of this function, residue at z is equals to 1, our function is equals to 1 by 2 here. Similarly, we can find out here about z is equals to 2 and z is equals to 3 here. So we can get at z is equals to 2, residue at z is equals to 2, our function f of z is equals to, we can get that solution is minus 4, and residue at z is equals to 3 of f of z is equals to 9 by 4. Now thing is that residue at z is equals to infinity is nothing but to find out that residue at z is equals to infinity, f of z should be right into the form of limit z tending to infinity minus z into our function f of z. Okay, so that is nothing but limit z tending to infinity minus z into, already we know that z square by z minus 1 into z minus 2 into z minus 3. Okay, so this is a limit z tending to infinity, so that is minus z cube by, so z minus 1 into z minus 2 into z minus 3 here. In the denominator we have to taking the common z into z, that is a z cube. So that is a limit z tending to infinity minus z cube by, so that is a z cube into 1 minus 1 by z, 1 minus 2 by z, 1 minus 3 by z here. So this z cube is cancelled now. So then automatically z tending to infinity, then automatically 1 by z which is tending to 0 here. So that is minus 1 by 1 minus 0, 1 minus 0, 1 minus 0. So that is minus 1. So the residue at z is equals to infinity, our function f of z is minus 1, and this is the extended complex plane. At the point of z is equals to infinity, that value equals to minus 1. So in the finite plane, so we can get at the point of poles, we can get 1 by 2 and minus 4 and 9 by 4. So we can add this the total residues of this extended and interior of that singularities, especially for that poles, we can add. Then what happened to, let us discuss here. So residue at z is equals to infinity of our function f of z, and residue at z is equals to 1, and residue at z is equals to 2 of this function, and residue at z is equals to 3 our function f of z. So that is, in the first one we can get 1 by 2 minus 4, 1 by 2 minus 4 plus 9 by 4 minus 1. So we can get that value equals to 0 here. So what happened here? We can get one theory here. One theorem statement is there. The residue at extended complex plane and interior of that singularities of residues, the sum should be equals to 0 here. So this is the residue at z is equals to infinite. Now So I am giving to our.
Yeah. Now we will see one last problem. See this. Integral over C e to the power of z by z into z minus 1 whole square, where C is the circle mod z equal to 2. Okay. This is one integration of a complex valued function over the circle mod z equal to 2. Now what are the singularities here? That see the denominator of the function z into z minus 1 whole square. So z equal to 0 is one singularity and z equal to 1 is another singularity, and z equal to 0 is not repeated, so it is a simple pole. Z equal to 1, z minus 1 whole square equal to 0 means z equal to 1, it is a pole of order 2, repeated 2 times, pole of order 2. And since z equal to 0 is a simple pole, we can use the formula, simple pole shortcut formula, limit z tends to a, z minus a into f of z. Let me utilize that formula. Okay. Now that is limit z tends to 0, z minus 0 into f of z, substituted f of z here, z is getting cancelled, and substituting limit z tends to 0, I am getting 1 value. Now for a pole of order m, we have the formula, already we know that. So using the pole of order 2 formula, this residue of at z equal to 1 is phi dash 1 by 1 factorial, that is phi dash m by m minus 1 factorial. Using that formula, residue at a pole of order 2 z equal to 1 is 0. Now residue theorem, as I said, residue theorem is integral value is equal to 2 pi into sum of the residues inside the pole. And one more important point, whenever we considering the singularities must be inside. Here the singularities are z equal to 0 and z equal to 1. Both lies inside the circle mod z equal to 2. Radius is 2 here, and the points are 0 and 1, which lies inside z equal to 2, mod z equal to 2. Okay. Now these are the formulae, the derivation of the formula for simple pole, right, and a pole of order m. Okay. And these are the shortcut rules to evaluate the residues. And then one more last important problem.
Yes.
You can see this, go through the PPT. If any doubts, you can post the questions. Thank you one and all.
And thank you, sir. Thank you for your topic, or you explaining very nice for our students. So the viewers and students, so maybe you are understood what are the pole and what are the singularities and what are the isolation singularities, and it is very important for. So thank you, sir. Once again I will thank you to our experts. Thank you for coming, sir.
Any
Thank you.
Any queries?